Today we are going to talk about how to use corresponding parts of congruent triangles in a proof. Copy down this important note. If you know that you have two triangles that are congruent, then you can assume that every pair of their corresponding parts is also congruent. Remember, when we're talking about figures like triangles, corresponding parts are things like sides that match or angles that match each other. Now, once you copy down that statement on your notes, you want to go to your Chapter 4 postulate paper and find the next empty box. The next empty box is called CPCTC. And this is a reason you're going to be using on proofs quite often today. CPCTC is really an abbreviation for a sentence that represents a math fact. CPCTC is an abbreviation for the rule that corresponding parts of congruent triangles have to be congruent. Now, I always like to see how quickly I can say the name of that fact because it's a bit of a math tongue twister. See how quickly you can say that. CPCTC. All right, now go back to your notes. CPCTC will make a lot more sense once you see it in action. Now, on the flow proofs you're going to fill in today, 70% or more of the proof is going to be exactly like the types of proofs you practiced in the previous lesson, where you use SSS, SAS, ASA, or AAS to prove two triangles are congruent. And then I'll talk about what to do with the one extra step at the end. So what I want you to do now is temporarily ignore the last box and fill in all the other boxes, just like the last lesson. You know that if you have two congruency facts in the given, you want to split them up into separate boxes so each box can represent one of the three congruencies you need to prove your triangles are congruent. Now, we need a third fact about equal sides or equal angles in our triangles. We've used up the given, so the third fact is probably something just from the diagram. Look at the diagram. Is there a pair of sides or angles you know have to match each other, just from looking at the picture? If you said opposite sides of an X, those angles have to match each other, well done. Mark that on your diagram. And then we're going to write that officially in our third box. So when you name an angle, when there's two angles that start at vertex A, make sure you use the three-letter way of naming the angle to make it clear whether you're talking about the left one or the right one. So you could call this angle CAB, or you could call it BAC. I'm going with CAB, and then congruent to angle EAD. The important thing is A, the vertex has to be in the middle of the name. The actual place where the V of the angle is always in the middle of the name. And your reason is vertical angles theorem. Now, a quick note that I should have mentioned earlier, anything from the given, make sure you mark it on the diagram because that will be very helpful later. Make sure you add congruency marks to show that CA is congruent to EA and then that BA is congruent to DA. Because that will help you on the next step. Look at your sides and angles that are marked congruent in one triangle and label them with S's for side or A's for angle. So now you're going to prove the two triangles are congruent. They didn't give us names for the triangles to use in the proof, so you use your own triangle names. The important thing to remember, however, is that when you name triangles, name congruent triangles, the order of the letters in the second has to match the order of letters in the first in terms of corresponding parts. So if you decide to name your first triangle CAB, because you started with C, you're going to have to start with E in the second triangle name. So if you call this one CAB, you'd have to call this one triangle EAD. If you called this one something like ABC, then you'd call this one ADE to match it. Now, at this point, you've labeled your sides and angles. Is that SSS, SAS, ASA, or AAS? If you said SAS, well done. Because you have a side, then angle, then side pattern of congruencies in each triangle. Now, the last step is the only step that's new today. You know the last step has to match what you're trying to prove, angle C is congruent to angle E. And here's the deal. The reason why we can prove that this corner C is equal to this corner E is because they're corresponding corners, matching corners, in two triangles that we just proved had to be congruent in every way. Because we stated that the whole triangle's match in every way, it makes sense that the corresponding corners have to match. In other words, corresponding parts, like C and E, have to be congruent to each other. CPCTC. So that's how you use CPCTC in a proof. You use it whenever the proof is saying go one step further from just saying the triangles match. After you say the triangles match, prove these two pieces of the matching triangles have to be congruent to each other. So if it's saying two angles match or two sides match for the proof, you probably have an extra step with a CPCTC reason. Try that on this proof. Anything in the given that's telling you a congruency has a congruency sign in it, that gets its own box. Anything in the given that's not giving you an equation, no congruency sign, like a little mini sentence here, kind of gets a prefix box because it will help you make an equation about equal sides or angles in a little while. All right, we have one equation about equal sides or angles. We need two more. This one must be something we can figure out just from looking at the diagram. If you look at the diagram, is there a pair of sides or a pair of angles that have to match? If you said that the shared side between the two triangles has to be the exact same whether you're looking at it as a side on the top triangle or side on the bottom triangle, well done. So add those congruency marks. If you didn't add congruency marks for the given, do that now too. And then we need to write this here. What would you write in this box? What equation can you make about those equal sides? ln is congruent to ln. What would your reason be? Reflexive property, something equals itself. So we have 2 out of our 3 facts about equal sides or angles. We need one more. Somehow we need to figure out one more equation about sides or angles from this mini sentence from the given. L is the midpoint of MO. Now, a good rule of thumb when you have a little sentence in the given like this, like midpoint or bisect sort of sentence, a vocabulary word sort of sentence, look at what part of the triangle they're mentioning at the end after the word midpoint or bisect and circle it. That is what you want to highlight on your diagram. Highlight MO. Now that you've highlighted MO, if L is the midpoint of that section, that's saying that L is cutting it into equal halves. Add those congruency marks to show that they are equal halves. And those equal halves can make our last equation about 2 pairs of sides in our triangle. So we could say the ML side on the top triangle has to equal the LO side on the bottom triangle. What would your reason be? Definition of midpoint. Anytime you see a vocabulary word, almost always, your next step will have reason of definition of the same word. Now, you have your 3 facts about congruent sides or angles. You've labeled those 3 facts on your diagram. Labels your S's and A's for sides and angle symbols in one triangle. It should look like that. So when you say your triangles match, just your triangle names might not be exactly like mine because there's more than one way to name a triangle. Just make sure that the order of letters in your second triangle name matches the order of the first. Like if you chose MLN, because you started with M, you'd have to start with its matching corner OLN for the second name. And then your reason would be SSS because you've got 3 pairs of matching sides in each triangle. Now what you're trying to prove is that corner or angle NLM here has to match NLO here. The reason why they match is because they're corresponding corners in 2 triangles that we already proved match. In other words, you could say angle NLM is congruent to angle NLO because CPCTC, corresponding parts of congruent triangles, are congruent. So you're starting to see the pattern here. 90% of your proof is the same as what you practiced in the previous lessons. You just have an extra step at the end to say, well, after I prove the whole triangles match, these two pieces of the triangles that correspond to each other have to match as part of two triangles that are the same in every way. This last one's a bit of a challenge question, but it starts off just like what we've done so far. So you know if there's an equation, a congruency of equal sides or angles in the given, it gets its own box. Anything that doesn't have a congruency sign, that's going to get a prefix box because we'll use that fact to make an equation in a little bit. Now for this box here, look at the diagram. And is there a pair of sides or angles that have to match just from looking at the picture? If you said the opposite sides of an x like that, always mirror each other, well done. So you could name those two angles, EBA and CBD. What's your reason? Vertical angles theorem. Well done. Now we're going to figure out how knowing that sides AE and CD are parallel help us make an equation about equal sides or angles. When I have a fact like this from the given, I go highlight sides AE and CD on the diagram. And then I choose one of the sides that connect the triangles, it doesn't really matter which one, and highlight that to work as a transversal. I'm going to choose this one. Now, if I just look at my highlighted lines, it's like two parallel lines with a transversal, and the angles between the highlighted lines here and here, the angles with highlighted sides, I know those have to be equal to each other. So I could say angle A is congruent to angle D. If you wanted to, you could call them angles EAB and BDC, but why bother? Just call them A and D. Since this is the only angle that starts at A, you can get away with using the one-letter version of the angle name. It's only when you have two angles starting at the same letter that you need to be more specific and use the three-letter version of the name. Now, your official reason for that, what sort of angle pair are A and D? If you said alternate interior angles, well done. Now, fun fact, this is actually one of the proofs that has at least 3 different ways of writing it. So, for example, if you had chosen to highlight the other line, you would have gotten that your alternate interior angles were E and C instead. And that would have been equally good. So this is an example of a proof that has more than one way to solve. All right, so now we have our matching angles and sides all labeled. We can name our triangles, make a congruency statement about those two triangles. Remember, if you name the first one, whatever order you choose, if I chose ABE, because I started with A, I'd have to start with its matching corner D in the other triangle, so you have the congruency marks. So if you go ABE, you'd have to name the next one DBC. Now, label your angles and sides with A's and S's in one triangle. It should look like that. So what reason would you write for saying the triangles match? AAS. Notice how it's AAS, not ASA, because a side is not between the matching angles like it would be with ASA. AAS because the side is not included between the matching angles, so the S is at the end of the name. Now, this is where it gets interesting. This is the part that really makes this proof a challenge question. We know what we're trying to prove, so we know our last step is going to be EC bisects AD. But how to get there? Because for once, our proof is not an equation. It's not like a congruency equation about equal sides or equal angles like the other two proofs. It's an actual little sentence. So how to get there? Well, a good rule of thumb is anytime you see a vocabulary word like bisect or midpoint, circle what's being bisected or being cut by a midpoint, and focus on that. So if we're trying to prove that EC bisects AD, that means we're trying to prove that AD is cut into equal halves. In other words, we're trying to prove that this half AB equals this half BD, because that's the same thing as being bisected. It means equal halves. So let's start by proving that, because that's a little bit easier. to prove than, say, proving a sentence like this. It's an equation, it's easier to get to. We could say that AB is congruent to BD because we already proved the triangles match each other. They're corresponding parts of two triangles we already said are twins in every way. So to say side AB in the first triangle is congruent to side BD in the second triangle, we would use CP-CTC. So this is one of the rare cases where CP-CTC is not in the last step because you use CP-CTC to prove equations, congruencies like this. Now that you've stated that AB is congruent to BD, then you could say that AD is being bisected where EC crosses it. And the reason why you could say that is because the word bisect means that AD is being cut in equal halves, and we just proved those halves are equal. In other words, our reason is just what the word bisect means. Definition of bisect is your final reason.